In this video, I want to show you how to take some functions and write them as power series. The nice thing about power series is they're polynomials, and we love polynomials. We can integrate them, we can take the derivative. They're very easy to deal with. So let's look at the one we know already. So we know we have 1 over 1 minus x is geometric series with our ratio being x. We know for this to converge, the absolute value of x has to be less than 1. This is also known as the interval of convergence, where it's so this would be from like -1 to 1. What if I have 1 over 1 plus x? I'm going to rewrite that as 1 over 1 minus negative x. So the key is I've got 1 over 1 minus something. That something is the same as our ratio. So this can be written as 1 plus negative x squared plus negative x cubed, yada, yada, yada. Writing this in summation notation, I have the summation as n goes from 0 to infinity of negative x to the n. The interval of convergence is the same because we want the absolute value of negative x to be less than 1, but the absolute value of negative x is the same thing as the absolute value of plain old x. This summation written like that looks like crap. We want to break it up a little bit. I want to be able to see that -1, pull it out. So I have -1 to the n, x to the n. So this is an alternating series. And it's equal to 1 over 1 plus x over its interval of convergence. Let's try a funkier one. What if I have 1 over 1 plus x squared? I pull the same trick. I write it as 1 over 1 minus a negative x squared. So I have that 1 over 1 minus crap. So that's my r, is that negative x squared. So that's what I'm going to put into my power series. Again, I'm going to break this up. I'll have -1 to the n and x squared to the n. So that'll give me -1 to the n times x to the 2n. This time, I want x squared to be less than 1, because that's my radius. Actually, negative x squared, but with the absolute value, that goes away. But if the absolute value of x squared is less than 1, that means the absolute value of x has to be less than 1. And what if it's not a 1 there? What if I've got 1 over 2 plus x? I will suck out that 2 and get it out of my hair. So now I have 1 over 1 plus x over 2. Which I can rewrite as 1 over 1 minus a negative x over 2. So that's my radius, negative x over 2. I'm going to keep the 1/2 out front for a minute, but I know that this expression, this 1 over 1 minus negative x over 2, can be written as the summation as n goes from 0 to infinity, negative x over 2 to the n. This I'm going to break up to make it prettier. Well, I think it's prettier. Actually looks kind of grosser, but it's easier to read. I can see that it's alternating. I've got x to the n on top and 2 to the n on bottom. Now that this is all cleaned up, I'm going to bring the 2 in. So that means I've got 1 extra power of 2 on the bottom. So I get -1 to the n, x to the n, over 2 raised to the n plus 1. This time my ratio is negative x over 2. So I want the absolute value of x over 2 to be less than 1. Which means the absolute value of x is less than 2. Now what happens if we actually plug in plus or minus 2? Well, if I plug in a positive 2, most of these 2's will cancel. I'm left with a single 2 on the bottom. -1 to the n over 2, that's going to diverge because you're just adding 1/2, subtracting 1/2, adding 1/2, subtracting 1/2. What if I stick in -2? Well, then my negatives will cancel, and I'm just adding up a bunch of 1/2s. Again, both of these will diverge. So my interval is just from -2 to 2, not including the endpoints. What? What if the shit on top? What if I've got x cubed over 1 plus x squared? Okay. Take a breath. It's not that bad. We're going to ignore the x cubed at first. Pull it out front. 1 over 1 plus x squared. I know what that does. That's -1 to the n, x to the 2n. So now all I need to do is pull this x cubed into the summation and multiply each term by 3 more x's. So I get -1 to the n, x to the 2n plus 3. Now, the cool thing about power functions, you can take the derivative of them and you can integrate them and they will have the same radius of convergence. So let's say we've got 1 over 1 minus x quantity squared. That is the derivative of the original expression we had of 1 over 1 minus x. So that means I just need to take the derivative of 1 plus x squared plus x cubed plus yada yada yada. So I have 1 plus 2x plus 3x squared plus yada yada yada. Yuck, I don't like it that way. I want it like this. If I've got x to the n, I can pull the n out front and subtract from the power. So I have n goes from 1 to infinity of n to the x to the n minus 1. Why did I change it to 1? Well, if n equals 0, I'm multiplying by 0. That's a non-term. I am going to rewrite it with n equals 0 to start because most of our power functions, it'd be easier to compare them if they all start with n equals 0, if we can do that. So here I've got n equals 0, so I'll add 1 to the n term and 1 to the power, making the n minus 1 into an n. So I have n plus 1 times x to the n. Natural log of 1 plus x, well that's just the integral of 1 over 1 plus x dx. Integrating that long expression, 1 minus x plus x squared minus x cubed plus yada yada yada, add 1 to the power, divide by what you get. I have x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus yada yada yada, and let's not forget the plus c. Writing this in summation notation, it's alternating, so I've got n goes from 1 to infinity of negative 1 to the n minus 1, x to the n over n plus c. I'll deal with this n equals 1 in a second. Let's deal with the c first. Now, if I stick x equals 0 into this expression, into the natural log, I get the natural log of 1 equals, if x equals 0, all these terms in the polynomial are 0. The only thing that survives is the c. So I have the net x equals 0, natural log of 1 equals c, but the natural log of 1 is 0, so thank goodness my c equals 0. So my summation now is n goes from 1 to infinity of negative 1 to the n minus 1, x to the n over n. I can rewrite this starting in with 0, and my negative 1 has to start with a 0 power, so that's good, negative 1 to the n. I add 1 to the n's in the fraction. What we'll be doing is taking what we know, taking the derivative, integrating, multiplying through, and massaging so that we can create more power series from the functions we already know.